is the definition of robotics, and that looks very boring. But as we know what exactly is robotics in this workshop, we can find a meaning to it. So, it has aspects of science, engineering, and technology, and it is basically a machine, right? A robot is a machine. But the actions it does, it can be a substitute for humans. So, we officially call robotics an interdisciplinary field, which integrates a lot of different fields, and computer science, electronics, electrical are the most sort of the fields. So, Harsh, can you move to the next slide? Yes, so all of you have already seen a lot of robots around you, right? Simple machines to very complex artificial intelligence robots. And I hope all of you know about humanoid robotics. There are a lot of robots which act like humans and move around, understand their environment, talk to us. And for a fun fact, you must be knowing that there's a robot called Sophia, and she is the first robot in this world to gain a citizenship from a country. So that's where robotics has gone. That's the heights it is reaching already. So it's definitely an interesting field, and uh, it's good to see so many participants who want to learn more about robotics. So there are a lot of different types of robots. There are industrial robots which work as machinery to move objects from one place to another for packaging on conveyor belts and uh, different works in the industry. There are robots in the medical industry, in hospitals, and near the patients. There are a lot of mini sized robots which are used for surgeries and operations. There are big robots which are used for x rays and such purposes in the labs. Then there are other types of robots which are based more towards entertainment, and like there's the humanoid robot, right? So it's a huge package of information. So you don't. I I would say that you can go over YouTube and watch some videos of some humanoid robots, especially Sophia, and you could say the way they answer human questions will make you feel that they have the whole world's knowledge packed in them. Okay, so there are a lot of different types of robots, and they definitely have some things in common, which are some hardware, some software algorithms, some particular circuitry. So, what is written in this particular slide is all those important things which are there in almost every robot, like the algorithms which make them move from one place to another, the motion planning, and how they understand their environment, and all of that. So that's what we'll do. We'll first look into the core concepts of robotics, on which every other kind of robot is based upon. Like I said, medical robots and entertainment robots, industrial robots, and a lot of them. So, can we move forward? Okay. So, I already mentioned some applications in here. Are some more. There are robots which help in fighting forest fires, which is something very, you must have seen the Australia forest fires, and a lot of such cases arise. So here is where the human numbers, dwindle, and we need more machines. So there are a lot of other applications in which robotics is reaching a huge heights. There are you can read this slide through and get to know what all is there. There are robots used for packaging. There are robots used for delivery. There are drones. Amazon is already using some drones for delivering packages, and there are drones used for surveillance and security. So yeah, Harsh, next slide, please. So, okay, this is the basic structure of a particular robot. What all is there in it? There are embedded systems, which are basically a combination of hardware and software, which tell robot how to, that is the base of a robot. Then there's computer vision that allows your robot to see like a human being. There is manipulation, estimation, and control. So basically, that is the part which helps it interact with the surroundings. to see what is there, to control the motion, to understand where to move and where to not. And then there's feedback control system, which basically is taking feedback from your environment and controlling your further motion according to it. Then there's definitely robot softwares. There are some codes, some algorithms written on which the robot works. For example, there's an industrial robot which has to pick something from place A and put it to place B. So it is already programmed to do so. That is the program which is written. Then there's human robot interaction. There's a lot of artificial intelligence used in it. There's robot kinematics and dynamics, which is how it moves. It has a lot of calculation behind it about which angle to cover, how long to extend out the arm, the mechanical arm, and further similar things. And there's firmware, which helps the robot with its security. There's sensing, and a lot of sensors are used. There are motion sensors, there are pressure sensors, there are temperature sensors, and a lot of different sensors which you will get to know. There's computing, and a lot of this is some of the most important aspects. There are some little concepts more embedded in a particular robot. It's one whole machine which acts like a human, so there must be a lot of different things added to it, right? So as we go through this workshop and the entire series, we'll get to know what exactly is there in a proper human-sized or proper industry-sized robot. Next slide, please. Okay, so here is okay. So when we look at the robot's design, there are a lot of different things. There are algorithms, and there's vision, there's hardware. This is the design part of a particular robot, which is there physically. You can touch it, you can feel it. That is the hardware design. And then there's the software design, which is the algorithms, the models on which it works, the motion planning, and the way it moves, the algorithms, the codes that are written, which on which the robot runs. That is the design. And then there's the implementation, that basically includes how the robot works on the design which is built upon it, which upon which it is built. So there's a lot of embedded systems, and there's some more programming into it. So the programming you're doing now, I hope you must be writing some codes. That is basically you're doing problem solving, right? You have some problems, you have to write a code which solves that problem. So robotics is another problem. There are a lot of questions and issues that you have to solve. So for that you write codes in different languages. There are some particular languages on which you write these algorithms and codes, and the robot runs on them. And then there's installation. There's a lot of testing and a lot of using before it is already into the market or into the workspace. And a lot of research is done into a robot to check if it meets the needs of the robot's user. Next slide. Okay, so this is a basic outline on what exactly is there on our level. So we are not directly going to write codes for a robot, right? We'll first segregate into topics that we know already. We know about electrical engineering, which deals with electrical and electronic parts of our robots. We know about computer science, which involves the coding part. So the algorithms which we write. So for example, there's an algorithm called SLAM, which is called simultaneous locomotion and mapping. So that is how that particular algorithm is used for a robot to make it understand about its surroundings and move according to them. Then there's mechanical engineering. A lot of mechanical engineering is used. We need to choose the right materials for the robot. We need to understand which part is connected to which part and how it works. For example, if we are using robots that work under forest fires, then we need to understand which kind of materials should be there, which kind of electrical components should be there, which can withhold higher temperatures. So a lot of engineering goes into a robot, and we can definitely segregate into different branches, and people from all these branches can come together, and then a robot is built. So it's not like one person can do the entire thing, which is shown in the movies. There are a lot of different fields of expertise required for one robot, as you can see. So these are the three broad categories at our level at BTech level, engineering level. So, oh yeah, next slide. Okay, so I would hand it over to the other team, which will explain about operator interface and ROS. Thank you.
Uh, Thank you, Dee. Hi guys, this is KL Rama. Hello, am I audible?
Yes, you're
Yes,
audible.
yes. Please continue.
Okay. Yeah, for making things, we discover many ways to get it done in an easy way. So for robotics, it is actually ROS. ROS is a robot operating system, which is a flexible framework for writing robot software. It is a collection of tools, libraries, and conventions that aim to simplify the task of creating complex and robust robot behavior across a wide variety of robotic platforms. Don't be afraid of the definition. It's just think it as an open source robotics middleware suite, which is not an operating system. You can consider ROS as a subway store where you can choose your own ingredients to make your own sandwich, which in our case is a robot. You can see the picture, which defies that. See, ROS is a actually is a subway store. See, you can take your own ingredients and make your robot, which in our case is our robot. Can you please go to the next slide? Yeah. Well, the point of ROS is robotic standard, so you don't need to reinvent the wheel anymore. We're building a new robotic software. Actually, ROS was created in 2007 and has now a huge and still growing user base. More and more packages are being developed. Actually, you don't have to create every robotic part in which we can use ROS to use the before parts which are already we installed in the packages. Yeah. Um, Also, a new version of ROS is about to be released, which is ROS 2. ROS 2 is a completely rewritten software and has many advantages over ROS 1. There is multi-platform support, embedded system support, and real-time execution, better resource handling. Like if you want to get into robotics, you should learn and use ROS, which is an easier way to learn robot. You mean implementation of a robot? Yeah. Uh, Actually, ROS is written in plus and Lisp programming languages. ROS has a built-in unit or integration test framework called ROS test that makes it easy to bring up and tear down test features, which is actually ROS has packages for everything. If you want to use your joystick even to control the robot, there is also a package for that. You can easily communicate between a Python node and a C++ node. Um, the open source simulators for ROS are VREP and Gazebo. Actually, ROS has great simulation tools. You can't always get your robot running for real, so you need simulation tools for your easy work. ROS has many tools such as and Gazebo. With Gazebo, you can even with Gazebo you can even add some physical constants. So when you run the simulation and the real robot, the outcome is pretty much the same. Without the ROS and with the ROS, the outcome is pretty much same. Imagine directly on your computer. That could save you a huge amount of time, right? Simulation tools also allow you to see and use other that you don't process for educational purposes or to the test in a specific environment. You don't have a robot and you want to use or just know about the functions of the other robot, you can get it done with ROS. If robots with ROS, ROS can work with multiple ROS masters. It means that you can have many independent robots, each with other ROS systems that all robots can communicate between each other. Actually, ROS is light. That means sources. You can quickly install the core packages and get started in a few minutes. Also, ROS embedded computers such as i3 boards, you can easily start a new project without much trouble. The softwares take 2 days, 3 days for downloading. ROS is not like that. It's easy to download, easy to install, and easy to run. When you build a robot, you don't necessarily want to reinvent or recreate every part. That's the before point. Yeah, you might want to focus on some development points and rest from other manufacturers. The goods, the one of the greatest strength of ROS is that it's open source. Yeah, it will go deeper. Likita will go into deeper by the video. Likita, thank you.
Yeah. Hi guys, this is Nikita. I'll be showing you a demo video uh, to show you how much ROS is important. Just a second. I guess you people could hear it, right?
Yes.
Yeah.
I really started getting interested in robots when I realized that I could write some code on my computer and something would really come alive. This robot is called Ernie. It makes a map of the garage just by driving around. And then based on the map, it can figure out where it is.
Ernie's creator is Rohan Agrawal, a high school student who's been building robots since he was 9.
ROS has really helped me personally because it's allowed me to make robots that I otherwise could not have.
The ROS that Rohan is talking about isn't a person. It's the robot operating system, and it's the underlying code that makes Ernie work. But ROS doesn't just run Ernie, it runs robots everywhere. The robot operating system came to life in 2007 at Stanford University and then moved to Silicon Valley incubator Willow Garage. That's where some of the smartest and wildest robotics thinkers, including Leila Takayama, had the freedom to pursue their ideas, no matter how crazy. And it did get a little weird. One of their biggest projects was the Personal Robot 2, or PR2.
PR2 was a big, honking robot. It was a 32-degree of freedom, $500,000 mobile manipulation platform, which was like, whatever. It was a very expensive robot that ran around and grabbed stuff.
PR2 was fun, and more importantly, it proved that the ROS code that ran it actually worked, but it wasn't all smooth sailing.
When ROS first got put on PR2, it was rough. And when things broke, it was kind of hard to fix.
Leila realized that ROS could be something bigger. Just like how Microsoft Windows made computers easy to use, ROS could open robotics to everyone. If only it weren't so fiendishly complicated.
One thing that I started talking with the team about was, we need other people to be able to use the code too. Otherwise, people aren't going to want to play if you make it too hard to use. So we ended up breaking down the code into usable bits and making sure that people who don't sit next to us could still use the code too.
Leila and the Willow Garage team tweaked and tinkered with ROS and eventually handed it over to a startup, Open Robotics, which used to be a nonprofit but now takes on commercial work. The company doesn't build robots. It develops the ROS software and hardware kits that people all over the world use to make their own. ROS code is packaged into different applications and uploaded to the web where anyone can download it for free. And everyone does. From giant companies like Intel and Qualcomm to military contractors and small startups. Mirza Shah is the co-founder.
Yeah. By this time, you might be clear with this point that just like Microsoft Windows made computers easy to use, this ROS made robotics open to everyone. So anyone with a basic knowledge could start making a bot. So if you get any problem in your PC, you won't going to code deeply and you need not debug it, right? You could just update it, or you could just take up some actions which your PC suggests. So this is a flexibility an operating system could provide. Even in ROS, you need, if there is any problem, you need not go into the things deeply and work it out. You could, that flexibility ROS can provide. And this code is also packaged into different packages, different applications, and it's uploaded into web. So if, for example, if one person code for a robot to see, for a robot to be able to see, and another person wrote code for arm manipulation, then the second person could download the first person's code and he could include vision feature in his arm manipulation bot.
Of Simbi Robotics, the startup behind Tally.
So the various tools that we use to build Tally, for example, the sensor drivers, the navigational algorithms, and the 3D cameras, those all come from ROS.
This oddball hangs out in the aisles at retail stores and can tell which products are in the wrong place, which have the wrong price tag, and what needs restocking. And that's what makes Open Robotics different from most other Silicon Valley companies. It relies on a community to make it better. The kids tinkering in the garage, new robotics companies, and tech giants who use ROS share their adapted code with other users.
Just like with anything that you put out in the world, more of the feedback is, hey, this didn't work, or hey, how do I use this thing? But it's just a different experience to be able to put it out there constantly as you're building it. ROS has a learning curve. You're really getting into the code and trying to figure out where the problems are, but it's always kind of exciting when it finally works.
Ernie is just a fun hobby for Rohan now, but someday the ROS code he used might end up in a driverless car or an autonomous lawnmower, or maybe something we haven't even imagined yet.
Yeah. So then we will move into just some of the topics of ROS briefly. As this is just an introductory session, we won't go into much details. We will be dealing with ROS in depth from our next part of series. But to give you a basic idea, a ROS package, the software in ROS will be organized in packages. The goal of these packages is to make everyone to be able to use it easily. It might contain ROS nodes. We will be dealing with ROS nodes in a bit. It may contain ROS nodes, a data set, third-party software, or anything else that logically constitutes a useful module. And the nodes, the node is it's just a piece of code that is used to communicate with other ROS nodes. For example, if you have a wall following robot, then one ROS could get distance sensor value and another node could control the motors of the robot. So these two nodes will communicate with each other in order to control the robot. So you could write entire ROS application in a single node, but having multiple nodes ensures that if a node crashes, it won't crash your entire ROS application. So it's like it's easy to debug and it won't. If the code is giving you an error, then you could easily check up codes one by one easily. But if you write entirely the entire code in a single node, then it's very difficult to debug it. So that's it's also used for communication with other robots to take information and so on. These codes will be we will be writing these codes of nodes in Python or C++. Thank you. That's it. Then we could, I'll share this to our next teammate.
Hi, can you hear me? Hello?
Yes, Abdul.
Yeah, we can hear you.
Okay, so I'll be starting again, like giving you a brief idea about what ROS is. Suppose you're playing a game, a computer game in, let's say FIFA 19. So when you're playing FIFA 19, you have a screen, you have your own joystick or controller, whatever you want to call it. You'll have a keyboard or a mouse if you're playing it on PC. So what the operating system does, if you're playing, suppose FIFA 19 on a laptop, so what the operating system does is it integrates all of your hardware components, such as your keyboard, your screen, and your inputs to give you an integrated output. So the user will not, so the user will have will be able to view everything in sync. So just like how the operating system acts when you're playing a video game, the ROS is the same thing for a robot. It integrates the sensor inputs, the decision making, and the actuators. The actuators could be motors or anything, whatever we like. So the basic block diagram of how a robot functions is that first the environment sensing is done, and then the robot plans as to what action is supposed to be taken. The planning can be based upon the code we write towards the robot to make it happen. So although like you are able to see 3 different block diagrams, we'll be focusing only on the first 2 for a bit like 3 or 4 slides from now on. So just remember that right now we are only focusing on the sensing and the planning part. We are not going to go to the actuator part where the robot does anything in real. So before I get started with all the codes and stuff, there are a few basic terminologies you need to know. You have already looked at what a node is, and it was explained to you. But just to repeat it so that you know we go in an order. So a node is something. A node is just a piece of code which runs over itself again and again. Suppose, for example, if you have an Arduino, and then the code, if you write a code for it, and then it runs over and over again. So that's a node. Or for those of you who have done C++, a node is just like, you know, a set of instructions with a for loop which never ends. It just goes on and on again and again. And then you have a publisher and a subscriber. So when you're using a robot, you'll have many different components, many different sensors, many different motors working all the way together. So a publisher is just a publisher could be anything which just sends information. You could have a sensor. Suppose it could be a sound sensor, and then the sound sensor will be just sending out information. So in that case, it's a publisher. Generally, all sensors are publishers. Then you'll have a subscriber. Subscriber could be a motor or anything. So the subscriber is what takes in information from the publisher. So this could be any of your output devices. You could have a monitor and everything, anything else. And then when we come about the data, we have looked at who publishes and who subscribes the data. But what is subscribed and what is published is about the data. So when we use ROS topic and ROS message, these two things are the keywords when we are referring to the data. So when you use ROS topic, it only refers to the name of the data being transferred. So when you use ROS topic, the computer will immediately know that you're referring to the name, not to the message. And when you use ROS message, it refers to the data being transmitted. So in this robot operating systems, you'll have you'll need a few programming languages. Although it's not necessary for this workshop, but you'll definitely need them. So we also make use of command prompt. So this QR code will lead you to a page which has a few basic command prompt commands for ROS. So you can look it up later. But for this workshop, this is not required. Then since we have looked at the 2 block diagrams, so this is something about the first one. So suppose when a robot moves from one place to another, it's essentially crucial for the robot to understand that there has been a change in position and there has been a change in the orientation of the robot. So we use odometry for this issue here. So odometry is just, you know, you use sensors and you use a few mathematical relations just to understand that the robot has changed its position or orientation. Sometimes it's not always accurate because a high reliance is put onto mathematical relations. For example, we have this robot moving in a straight line here. We have a robot moving in a straight line here. So suppose if you want to understand the distance the robot has moved, you could just multiply the diameter with the number of times the wheel has rotated. But suppose if this robot was to be moving in a very slippery environment with no friction at all, so the wheels could skid, and so then the robot would not know how much distance it has moved. So this is the reason we use different sensors like a camera or a GPS to understand more precisely about how the robot is moving. So we have an example here. We have made a robot which is supposed to move in circles. So we have assigned the velocities Vx, Vi, and Vth. And this second image shows you about the number of times the code is to be repeated. Meaning, so over here, one means it's going to be repeated one time every second. It could not be ideal, but we are using this. So with all the mathematical relations you have learned in your high school, so we'll using these cos and sine, we can understand the distance the robot has moved and its orientation at any particular point. If you do not need to actually understand what each line is doing here, but you just need to get an overall image about what's happening. So so we have given these inputs about how the robot has moved. This is for the mathematical relations we have given to the robot. So when we run this command in the command prompt, so you will get the distance the robot has moved. So here x, y, z in the linear direction and angular direction in x, y, z. So this is the kind of output you'd be expecting if you run this function. So you can find more about this topic in these two QR codes. The first one will lead you to WikiROS. So over there you'll have a complete description of all the codes I have pasted in the PPT. You need not understand everything, but you just need to have an overall image. Next, we'll be moving on to how the robot actually detects the distance. So yeah, a camera is not feasible for a robot to actually understand the distance which has been covered. So we use a laser scanner. Laser scanner converts the 3D environment to the 3D environment that the robot is able to understand the 3D environment as it is. Had we been using a camera, the 3D environment would have been changed to a 2D environment, which would not be of any use to us. So how this laser scanner works basically is a laser beam is sent out. It is reflected across any surface. It could be any obstacle in the robot's path. And then the reflected ray is captured by a sensor. So using the time since the laser was sent out and the laser was received, will be able to calculate the distance from the robot till the obstacle. So here are a few parameters we need to consider while selecting a laser scanner. So there are 7 parameters. So the minimum angle is the rightmost angle the laser scanner can scan, and the maximum angle is the leftmost. Then we have angle resolution. If you look at the image here, the robot is sending out multiple beams. Angle resolution is the difference between any two beams. Is the difference of the angle and between any two beams. So the lesser, so the higher resolution would mean that there is a less angle difference. There's a less angle difference between any two beams. So it could be useful for you. And then the time increment and scan time. These are two different parameters. So time increment is when suppose the laser scanner sends out this one beam, and then the time increment is the time required for the robot to send out the next beam after it. But when it comes to scan time is when it starts all the way, the laser beam is sent out all the way from here till there, till the end, and then once again. So scan time would mean 2 images. So maximum range and minimum range is to the distance the robot can measure. So when all these parameters are running, the laser scanner gives out two inputs. They both are in form of arrays. It's the list of intensities of the laser beam return, and using that we calculate the distance till the obstacle. So this is the type of code you'll be looking into. So notice here we have used ROS topic, indicating that it's not the message, it's the name of the message which we are more interested in. So these are all the output information would be expecting from a laser scan. So these are two QR codes. You may refer them whenever you want. So now, so far we have looked at how to understand the distance moved and the distance between an obstacle. But now we need to understand the velocity of the robot. So the velocity is measured using a robot sensor. So here we have a robot moving in circles. So you run this command in the command prompt, and this is what you'll be looking at as the result. So the linear velocity represents the distance moved according to every axis, while the angular indicates the rotation. So once you have understood that the robot will be moving in a particular velocity in whatever direction you wish it to be, it's also important to give out the velocity commands, because you'll need to do that. Trust me. So if suppose we want to make a robot move in a linear direction for about 0.5 meters per second, this is the type of code you'll be looking at. So we are declaring the linear velocities in the first section and the angular velocities in the next one. So, and this 3 over here means that it has to be refreshed 3 times every second. So notice that all the angular velocities are 0 because the robot is not rotating. So once you run this code, this is the type of output you'll be expecting. So the robot is moving in a straight line. But how if you want to make the robot to rotate in whatever direction you want, so all the linear velocities will be 0, and the angular velocity with respect to which axis you want the robot to rotate would be of some number. So here this number has been chosen to be 0.3, and the robot is moving in I don't know what's this is anti-clockwise direction. So suppose if we set this z value to negative 0.3, the robot would be moving in the opposite direction, which means the clockwise direction. So I think I'm done here. So you have any questions?
Okay, so we can move further on. Harsh, please, can you start presenting? Yeah, 0.3 inches basically. That's like a value which you have mentioned as a question. Okay, so now we'll be looking upon manipulators and effectors. So manipulators and effectors are basically mechanical components of a robotic system. Like all the as you got in introduction, there are many like different streams in robotics. So mechanical engineering is a powerful and a requirement stream to build up a robot. So manipulator is basically an mechanism which is controlled through some electronic control systems, and it consists of various segments called as links. Basically, this mechanism will interact with the environment is nothing but the and it will interact with environment to perform the specific task which is being given to it. So it is nothing but a mechanism like which is consists of various links, and it will perform and complete its task. So that is what a manipulator is. As you can see in the image here, we have some of you robotic arms. Like you must have seen various videos these manipulators are used in factories to automate things. So here you can see the see two images, and they have specific applications which are specialized in their own region. Okay, we'll move forward to the end effectors now. Yeah. So end effectors are basically the last link of a manipulator. So that is where your the robotic system will basically interact with the environment. Like that is the touch point, you can say. So end effectors can be of various type. It can be hand based, like as you can see here in the image, we have hand based end effectors. So it depends on all the application. Like if you want to pick up something, so you can pick up using some vacuum suction pumps, right? So that can be an end effector. So you can have that sort of end effector. Then you also, if you want a specific thing to be taken up, so we have a hand type of end effectors. So its strict definition is basically the last link of a manipulator. So there's where your robotic system will basically interact with the environment and perform its task. Okay, we'll move forward. Yeah, now we'll talk about robotic locomotion. What is locomotion is nothing but traveling from one place to another place. So without this, basically your robot can't move, right? Your robot requires something to move. So robotic locomotion uh, is a collective name for various methods through which the robot can transport from one place to another place. So there are various types of robotic locomotion. Can you move on to the next slide? Yeah, so we'll discuss a few in brief here. One is the legged locomotion. So this is basically a bit difficult type of locomotion because you just imagine your own feet, right? So there are so many joints. There is a knee joint, then you have the joint at your ankles. So all these needs to be basically all these needs to be connected through motors. So it's a bit of complex type of locomotion, but it has been implemented very well by Boston Dynamics. You can look for that up and you can check out their videos. They have actually made a few humanoid robots which have a leg kind of a locomotion. We have next also there's a common locomotion, the wheeled locomotion. It's pretty easy to implement this because there won't be large number of motors, right? You just need to power up a motor and run the wheels. Okay, can we move forward? Yeah. We also have this clip and skid mechanism. So if you guys know tanks, what army tanks are, what they have is basically chains around the wheels, right? So using the chains, the like the how they move is by slipping through the chains. So that is one kind of locomotion which is used popularly. If you know the Mars rover, so that has the skid type of locomotion which is used. Then we have the flight locomotion, which is actually like you can move around in space, right? By flying, someone is flying, jumping. So these are some modern types of locomotion used based upon some biological systems like frogs. So what the robotic engineers do is they study these and then they study what type of mechanism has to be built up and they work upon. So at this point of time, I have one question for the crowd. So are drones robots? What is your thought about this? Like, are the drones robots? What do you guys think? Anyone volunteering to answer?
Yes, they are robots.
Okay, who was this? Hello?
Yeah, hello.
Yeah, just can you explain why do you think drones are robots?
Because they have a mechanical moving parts, and these mechanical movements are controlled by system software. They're having some electronic feedback control. So all the elements which you have mentioned in the robotics definition, they are present in drones.
Okay, this is a very valid point, but the thing is, not all drones are robots. Like there are what basically a definition of robot is, it has to be autonomous, right? but there are some drones which are controlled only using your remote control, that is RC control drones. These are not, these can't be technically termed into robots. There are some semi-autonomous drones which have their own AI and the controller also. These types of drones can be termed as robots. Okay, so this is pretty clear. We'll move forward with the algorithms part now. Harsh will take on the floor now. Thanks.
Hello everyone, I am Harsh. I will be taking the part of programming and algorithms. Okay, so the most widely used algorithm is SLAM, that is simultaneous localization and mapping. So what SLAM does is it's like it creates or updates the map what is created by using localization, and it creates a map with an unknown environment while simultaneously keeping track of the position before which it has moved. So let's see what is exactly. So it estimates the pose of a robot. So what the pose means, it is a combination of two words. The first one is position and the second one is orientation. So what it does is it tracks it counts the distance it has moved from the initial position. So the position means it can calculate the x and y coordinates. So suppose it is at the initial position it was at x comma y. So after some time it has moved to x1 comma y1. So it can calculate the position of the robot at this instant. But what about the orientation? I mean, if it can be in any angle, right? With respect to the z-axis, it can be on any angle. So for calculating the orientation, we are using z-axis. So there is an angle between the axis z-axis and the angle of the robot from the x-axis. So this is what orientation is. So the pose is the combination of position as well as orientation. So what the SLAM do is estimate the pose of a robot and the map of the environment at the same time. So before what we were doing is we have to calculate the localization. It means the position on orientation, that is pose of a robot separately, and then we have to create a map. So that was some of time taking, and it was not a good to do these things. So if we want robots to be more reactive, so we want both of things to be done at the same time. But these two are like egg and chicken. Like we cannot tell which one we have to do first. Both are dependent on each other. Like a map is needed for localization. If we have to localize, you have to find the position of a robot. We need the map, and to find the map, we need the position. We need the localization. So it is like egg and chicken problem. So to solve this problem, what we have is we have some algorithms, some approximate algorithms. The most common one is known as KL algorithm, that is Kalman and Kalman filter. So this algorithm we use to solve this problem. So we won't go in much deep in this workshop. That things we will cover in the later one. So you have understood what SLAM is. It localize and creates map simultaneously. It do both the things at the same time. So what localization is? Inferring location given a map, and mapping inferring a map given locations. So SLAM is learning a map and locating the robot simultaneously. So it do both the things at the same time. So what are the applications of SLAM? So SLAM is centrally used in indoors, outdoors, and in air and underwater applications. So these are autonomous or manned also. So the examples are at home, we can see the vacuum cleaner. You have seen on Amazon that you can have a Roomba. It's called Roomba. So you can search on Amazon, you can see a vacuum cleaner. So that's an example of application of SLAM. And lawn mower, air surveillance. For air, we use surveillance and unmanned air vehicles. In underwater, we have reef monitoring. In underground, exploration of mines. And in space, these are used to terrain mapping for localization. So mostly we'll be going through the at home, like on the land, which we are using on the land. So we won't go on deep with air, underground, and space one. There are basically two types of SLAM. The first one is visual, and the second one is LiDAR. So what the visual one is, visual SLAM is camera. So to see things, we need something to see the surrounding, right? So for this, we have camera. So we use camera and we use computer vision to to let the computer see how we humans see. So it's like first we have a camera, and in that we will get some points. So that are called set points. So set points of interest determined by the algorithm. So we now connect that points with the edges, and using those points we create a 3D map. So this is used, or this is being done with the help of computer vision, and for this we require a camera. So now this, using computer vision, you know there are some errors, like there are camera, it depends on the resolution of camera as well, but mostly there are some noise and all, so it is not much efficient. So there's another method is lidar slam. So what lidar slam is, light detection and ranging. So what this uses, it uses laser sensors. So what IMU is, it is inertial measurement unit. What this consists of is accelerometer and gyroscopes. What it does, it calculates the distance from the initial position and the orientation. What odometry is, what localization is. So it does the same thing. And okay, so lidar is like, it uses lasers, so it is more accurate than the uh, vision slam. Why? Because like in sorry, excuse me. Yeah, so lidar measures distance of an object by illuminating the object with the multiple transceivers. So what it does is it it gives the laser light, and when it lights after the object, so it will receive at the receiver. So it will calculate the distance. So we have the time, like when we when we release the laser and when we receive the laser. So we have a time, and we will calculate from that the distance. So through this we can do it more efficiently. We know the exact distance of the map. We know exact position of the obstacle. So, and this is very fast, because you know the speed of light is, I mean, speed of light laser is almost equivalent to speed of light. So this happens very fast. So because of how quickly light travels, very precise laser performance is needed to accurately track the exact distance from the robot to each target. So this requirement for precise makes lidar both a fast and accurate approach. So this approach of algorithm solving SLAM, this is the most fast and the accurate one, because we are using laser. But this is a kind of more expensive, because in cameras we can have we can do cost cutting and all those things, but in lasers we need accurate, and so this is somewhat expensive. Okay, so then we move to the sensing and perception. This will cover by another team.
Okay, hey guys, my name is Meghna. Kaushik and I will be covering sensing and perception today. Thank you. So we've learned so much right now, a lot of overwhelming topics, but I believe sensors is the one we can relate to most because it's based off of us, humans. So what exactly is a sensor? Why do robots need it? So like it's mentioned, sensors are used to estimate robots' condition and environment. A robot is given a certain task, and it can only complete if it has enough information about its surroundings and where it's located. Any sort of small task, even if it has to walk a certain distance, it needs to know, can it really travel that far without any collisions or any damage to the environment? So we're going to talk about three major topics. First, the robot needs to know what exactly is happening around it. At this phase, it doesn't determine what exactly is around, but it just knows it has a general idea of its space. And the second one is when it starts actually identifying the objects, like, oh, there's a ball next to me. Oh, this right now, next to me, there's a water bottle. And then the third step is when it just determines how to interact with all these objects and complete its task. So starting with the first one, where am I relative to the world? It's similar to humans. We wake up in the morning, we need a moment to figure out what exactly is happening around me, like a sense of space. So robots use sensors like stereo, range, acoustics, and localization. These are just a few examples for how a robot figures out where exactly it is. So in a stereo sensor, it's sound. So from the left side and right side, just at least two sensors, it determines, is there any noise coming? And that just gives it an idea or something for it to figure out, is that something I should be concerned about? If there's no sound, it can proceed with its task. If there is, it might pay attention and be like, okay, there's something on the left side of me, or there's something on the right side. A range sensor, it's pretty much what it sounds like. It determines the distance and space around it. Where exactly is everything around me? And acoustics, if you tie it with our stereo, it's kind of like, it has it's a different variety of sound sensors, and stereo is kind of like a technique. It's like kind of a branch underneath acoustics. And then after mapping, like we were mentioned right before this, localization and mapping, it's kind of helps the robot figure out, kind of lay out a grid of what's happening around it. So now that the robot has figured out exactly what's going around near it, it needs to figure out what exactly is the sound, or what am I seeing? And this is the second step, what is around me? So similar to how humans use our senses, right? We see stuff, we hear, we smell, we taste, like that. Robots also use vision and sounds and sensors on the body, external sensors, to figure out what exactly is happening. It uses light probably for vision to get an idea and try to, based on the reflection, try to process that information. And all this entire steps, all these are just for the robot to learn what's happening. We humans, that's pretty much how we also grow. We get an idea of what's around us and start connecting all the dots to form images in our head and process the information. And robots are doing exactly the same thing to make sure it can carry out the task that it was assigned to do. Reaching out to the next part, after all this information has been processed, right? It knows where it is, what exactly is around it. That's when it decides how to exactly interact with the objects. For any small task, even if the robot just has to pick up a ball or it has to move a box to a certain place, it needs to figure out, okay, I know what the object is and I know where it is. I need to know how to get to it. Is it possible to get to it right now, or do I need some sort of more information? Once it's figured all of that, it gets to the object and then it decides how to interact. And this is the sensors on the tips, or like whatever feature we need, like legs, on the legs or on the hands. And the sensors, like touch tips at the end of the fingers, help it come in contact with the object. Similar to when we pick up a phone or anything, where fingers are the first thing that touch. So this robot's based on the same idea. So the end effectors on the tips of the robot help it pick up. In this case, you can see it's helping pick up a beaker to transfer a liquid into another beaker. And for that task, it needs to know exactly how much force to apply and how far do I need to move the arm to get to that, and where exactly should I hold it. All these are features that we would put into the robot. Like all this programming would involve entering all that information, but ultimately the robot needs to have all this information to carry out that task. Next, Kaushik will cover perception.
Yeah, thank you. So hey guys, I'll be telling you about the perception part. And so right now you just heard what are sensors and what do robots have to do with sensors. And we all know that any task that the robot has to do, it has to sense what is its environment and what is the task to be done and everything of that sort. So after the robot senses, it then carries out the task. But what is the intermediate part in the between? It should be able to perceive or understand for as to what the sensors has given, what is the input data the sensors have provided to the robot, and according to that it should be able to perform the task. So this is that part where the perception plays a role. So what is this perception? So once there are different kind of sensors, as already Meghna has explained to all of you, the acoustic and stereo and different types. So after information is inputted from information is provided to the robot via these sensors, the robot plays a role where it has to understand what are its surroundings and what kind of environment it is in currently, and according to that it should act. So here this plays a really crucial part in the robot's development, as there are many chances for us this part can go wrong. And suppose there are, nowadays we are seeing many autonomous cars and automatic driven cars and bikes and all, which are being developed by many companies. In this there are sensors part in which when the car is moving on the roads, it should be able to sense if there's a sudden a kid or a person is coming in front of it. The car should be able to sense, okay, there's a person now, I should stop it, and something like that. So this is where the perception plays a part, and it should be coded very perfectly when it comes to the robot. So this is that part which deals mostly with machine learning algorithms and artificial intelligence and all. The coding part mainly plays a role here. Okay, so once the information is sensed, or once the sensors give the input, what the robot does is, you have already seen the camera, lidar sensors, stereo sensors, sonar, and all. So once the information is received by the robot via the sensors just give the information. They don't actually tell the robot what to do. It all depends upon the robot's coding and the programming inside that plays the role. So after this information is received by the robot, it does a mapping or a 3D kits for us to where the robot is currently, the location of the robot, the surrounding of the robot. Suppose we see, we have given a task to a robot to pick up a glass of water. So after this task is given, first it should sense, okay, this is the task that has been given to me. Then it should check the surroundings. Okay, where am I and which direction should I go? What is the path which I should take to reach the glass of water? After reaching that, okay, where is this water? Will my hand be able to reach it? Then how should I hold the glass? Is it should I suppose, if the robot has hold the glass, is it tight enough so that I can pick it up, or is my hold a bit loose? Something like that. So all this part actually is the perception part, where the robot understands at each and every step. So whether the task given to us, it is being performed properly or not. So that is where the perception plays a role. And after the mapping, the 3D grids are done, the information is extracted. Like, see, as I've told you, understanding from these mapping and 3D, what is this mapping and 3D grids actually? So after the robot actually plots the information inputted to it. Like, there'll be a 3D kind of grid, or a image that will be running inside the robot. Then that will actually tell the robot, okay, I'm in this location. Beside me there's a stool, and in front of me there's an obstacle I have to cross. That everything, according to this, it will extract the information, and from that it will perform the task. So this is what the perception does. And after this, AI, we give the proper algorithms and AI into the robot. It should be able to execute properly the task. And obviously, while doing the task, proper navigation should be done and everything. So if there's a sudden obstacle, there's a sudden ball coming into the path of the robot, it should be able to sense, understand, and try to uh, avoid that obstacle and something like that. So this is the perception part. So next slide, once please. Yeah. So coming to this, there are actually different types of perception. So we'll see a few of them. One is this computational stereo. So, okay, what is this computational stereo? I guess we have all tried a very weird experiment in our childhood. Once seeing the same object with once a right eye closed, then the left eye closed. So even if you try it now, you actually realize that if you see the same image once with the left eye and then with the right eye, you actually observe that you get two different angles of that image. Okay, so why is this happen? Because the right and left eye are at different parts of your face, so there are different angles of viewing that image. So coming on to biological terms, we know that the brain processes these two images and provides a proper image, something like that. We all know that, we might have studied. So the same thing. So when it comes to computation stereo, this is actually involves the 3D mapping, which I was referring to. So the cameras actually, or the sensors you call, on the robot, they actually uh, take the information, or they gather the surroundings information and provide it to robot. According to this, the robot gives a 3D view of everything that is around it, and it understands the kind of location it is in. Okay, and this is one thing. And talking about motion tracking. Okay, now what is motion tracking? Everybody is actually very fascinated about Iron Man movie, all the Marvel movies and all. So if you have actually seen videos, you'll observe that the person who plays Iron Man, he doesn't wear an action suit on the sets. There's some kind of special suit which is as, and this suit actually the computer, when they're shooting this and framing them, when in this, the suit is automatically added to the person's body. So how does the computer do this? For that, it should understand the actor's movements. Okay, when it is the actor is supposed to, if the actor is raising a hand in a particular scene, the computer should be able to realize this hand is raising, and according to that, the suit's movement should also be judged by the computer, and according to that, the frames are done, the scenes are made, the graphics are added to that. So this part is where the motion tracking plays a role. So as you can see in that image, the man is about to move, and you see the other, the second image is the one which the computer has drawn as reference to the man, one with small blue color dots in between. It has actually uh, uh, classified the man's body in terms of this part, so you can understand the movement very easily. So this is what is motion tracking. So every object generally, the robots generally, when they see a person or an object that is moving, they classify that as a stick image or something like that, so that they can understand for us to how the movements are made. So that is where the motion tracking plays a role. And also, once, can you just show the previous slide? When it comes to feature, yeah, next slide one. Yeah. So no, before one. Yeah. So feature detection. What is the next two slides? No, the same one. Next one. Next one. Yeah. This one. So feature detection. So you also have seen the feature face recognition examples nowadays in many security systems and all. We show our face and recognizes who is us, who, what. So what's their identity and something like that. So this feature recognition is something that is uh, that plays a role here. So when our face is scanned by the robot, what it does is, after the scanning is done, it will actually divide our face into first a basic view for us, the shape of the face, and then it will classify each of the features. Okay, how, the eye shape of the eyes, the distance between the eyes, and everything like that. So this is the feature recognition part of it. As you can see, suppose an example, there's a plus symbol in green color. So after that part is sensed by the robot, it is able to draw only the outline of the plus. So you can see this feature recognition is a part where the robot understands each and every part clearly and then gives a particular idea of the, but it processes the input data in a much more better manner, clear manner for it to perform the task. And when it comes to visual data or something related to computation stereo, as you can see in the fourth image. So yeah, there you can see here that two cameras are actually giving the image or the uh, 3D mapping view of the block, and it is then instructing the robot to pick it up. So what the robot should do now is actually place its arm in such a way that it exactly holds the block with the required force, and then it lifts it clearly. Suppose the robot is given a task to open a jar, and first it should place its arm on the lid, then give the necessary torque in order to rotate the lid, and then remove it. So all this part is actually the perception part, and the tactile senses play a very important role at this moment. So at every stage there'll be a sensing part and the perception part for the robot. It should understand what to do next. Suppose it is about to rotate the jar and suddenly it slips and falls down. It should be able to, okay, there's a, then the robot should be able to understand, okay, there's some problem in my task or my execution of the task and something like that. So at every stage there can be other circumstances which can try to obstruct the task of the robot, and at every instant it should be able to understand what is the current situation and give, and according to that the robot should be able to act. So as you can see, this sensing and perception part is a combined part, and after the sensors, the perception part. Uh, this is how the robot actually understands and performs the task. Sensors give the input to the robot, and the robot processes this information. They are interlinked. And next, I will give it to next person. Sujana, I guess he's going to be present your screen and.
Hi guys. Is my screen visible?
Yeah, it is visible.
Okay, so hi everyone. I'm Surya from EA HAM Club. So now, we have seen the basics, or like how to start robotics and everything. So basically, what we are planning to do, like in the upcoming days, is we'll be participating in the robotic competitions which are held every year, like in various institutes So we'll be focusing on them, and we'll simultaneously be learning the topics like learning by doing. So we will now like discuss about some of the robotic competitions. So first we have, this is Robocon. So robotic contest, in short Robocon, like it is an Asia Pacific Broadcasting Union organizes it. So all over the 20 countries from all over the Asia Pacific region will take part in it. So generally in it has only one team representing a country. So generally in our country, like Doordarshan organizes it. This year we have IIT Delhi conducting it. So it is like an international competition, and the task which they give is really challenging. So you can understand the potential, like only one team get to represent the country. All the teams inside the country, like they will be screened in the IIT Delhi competition. So then later you will be taken to the final one, which will this time it is held in China. So we will see the first we will see the statement for this year. So here it is. So it is conducted in Jimo, China. Let's see the problem statement. Can you hear this? Can you hear the audio?
No.
No. Okay. Is it audible now?
No.
Hello. Wait. Just a second. How to share this audio, Harsh?
I guess when I was sharing, then also it was not audible.
Okay, so let's
Yeah, Likita, can you share? Like when you were sharing, we were able to hear. So if possible, can you share now?
yeah, I'll stop sharing.
I can share.
Yeah.
Okay.
Just a second.
So the task which we were given this time was throwing, Robocon is 20 years this time. So it was conducted from the past 20 years. So as a part of that, they are planning to use two robots. Like in China, we have a festival, if someone becomes 20 years old, they consider him as an adult. So they'll be having some party type things. So there they will be throwing, they'll be having a game in which they'll be throwing arrows into a pot. So they asked us to simulate this thing using robots. So that was basically the theme. So yeah. Not audible. Okay, it's not audible. So this is a thing. Every team has two robots. One is for throwing the bot. One is the throwing robot TR, and one is the defensive robot DR. So they'll be. This is the region where we have to do the task. You play, Likita. You don't stop it. I'll be telling. So here is the region. Like this is the region where our bot should only play. So every team has 20 arrows. They can, like, the robot can take the arrows and it has to throw one by one to the pot. So the robot, we have 3 minutes for the game. The robot which will complete, which will throw 2 arrows into all the pots will be winning. So if not like that, if no robots can throw it into the 2 bots, so they will be considering the maximum point. So this defensive robot can enter into the inside region of the area. So it can disturb the other bot throwing this thing. This TR cannot enter it. It should be only outside the bot. So that TR only should, TR can throw arrows into the bot. So yeah, you see this. After the arrows on the TR is completed, it can take 1 arrow or it can take all the arrows at a time. If all the arrows are exhausted, the defensive robot can help it to throw outside the arrows so that the TR can take it and reuse them again. The defensive robot can disturb other arrows also. So the team completing this, we'll be having 3 minutes. This is just the animation. It need not be, it is just an animation to show the rules and everything. This video is for that, but practically we have to make these type of robots are not possible now. Maybe in future they are possible. So generally we have to analyze the strategy and we have to make the robots it should be having a manipulator and it should be having image processing. So the things we discussed, it should be locating the pot and everything should be done by ourselves only. So this is the challenge. So this is I should say this is really tough challenge. So that's what one team from the country itself shows the competition. So if you are interested, you have time, February 18 is the thing. So we have more 4 days. One team from our college is, this time they are applying for it. So yeah, next slide. Likita, I'll share, you stop it. So however, there is no audio, right? Okay, you can see it, right? Okay, so next we have E-Yantra. This is also one of the popular robotic competition. It is conducted by Computer Science Department of IIT Bombay. So it is also one of the famous robotic competitions conducted in India. So many teams participate here. So before in E-Yantra, what happens is while you are registering for the event, for every team we have 4 people. So they'll be asking our areas of interest and everything, which area are you expertised. So based on that, they'll be allotting a theme. So every team has 2 stages. First, they'll be giving us the resources, where to learn from the basics. So learning ROS, installing Ubuntu and stuff from the basic thing they'll start, and they'll be taking it to the highest level. Like it will take around 2 months. So they'll be screening all the teams in these 2 months. So they'll be conducting like they'll be giving various tasks. So they'll be screening them. After that, once the teams are finalized, they'll be taking into the final competition conducted at IIT Bombay. So the teams which we got this year were first one is the Nirikshak bot. So this bot includes like if the team members are interested in this image processing, control systems, 3D designing, algorithm building, and simulation and Python programming. So this bot is given like based on their choices. This bot will be assigned to them. So this is basically, you see, right? It has to perform image processing and these things. So this is about Nirikshak bot. So we have more bots, like more themes. This is Sankat Mochan bot. This, like if you are expertised in FPGA communication, sensor interfacing, so then you might be assigned to this thing. So yeah, next we have Sahayak bot. So like this time we like two teams from our college participated. One, like the team in which I was there, got this Sahayak bot. So basically we have ROS, 2D mapping, 3D mapping, and autonomous navigation, like the previous slides you were shown. So this was the thing. So basically this, we were novices to ROS, so we got this thing. So yeah, this is the Sahayak bot, and next one is a Vargi bot. So here we include robotic manipulation, robotic perception, IoT, Google app scripting, Python and JavaScript. So this this robot is related to that. And finally, we have Vitarna drone, sorry. So this is the, like other team got this thing. So this includes control systems, path planning, image processing, and you see this is a drone, like more cool stuff types. We have to simulate this thing in Gazebo. Gazebo is like an online simulator for the robot which you are going to make actually. So this was the thing. It has to pick the things like address. It has to, drone delivery speed. So this is basically drone delivery. So here is the task, like from the Vitarna drone team. So you can have it. This was developed by the team from our college only. So you see the control systems and stuff related to this. There is no audio for this. Okay, so not an issue. So it has to pick the courier or something. It will take to the